On July 22, 2026, a 30-meter-tall rocket ignited in the East China Sea, throwing massive V-shaped plumes of smoke across the water. This is Gravity 1, built by the Chinese aerospace firm Arianespace. It holds the record as the most powerful solid propellant rocket in the world. Building a 405-ton explosive device is difficult enough on solid ground. Private space companies are now moving offshore to fire these vehicles from the deck of a pitching ship in the middle of the ocean. This globe highlights the problem. Traditional land-based spaceports are geographically locked. A fixed launch point severely limits the available orbital trajectories, often requiring rockets to burn extra fuel to reach the correct path. There are also safety hazards. As a rocket climbs, it sheds its heavy, spent fuel stages. Launching over land forces engineers to calculate restrictive drop zones to ensure these massive metal cylinders avoid populated areas or commercial airspace. Today, the demand for orbital real estate is surging. Companies are building mega constellations, networks of thousands of interconnected satellites, which require a continuous launch schedule that land bases cannot safely support. The commercial space industry is moving offshore to eliminate the geographic limitations of terrestrial infrastructure. A mobile sea platform acts as a geographic workaround. By putting the launch pad on a ship, engineers can sail the infrastructure to the optimal coordinates for every mission. This diagram illustrates the physical advantage. By sailing a launch platform to the equator, a rocket hijacks the Earth's maximum rotational speed, gaining a free boost in velocity that increases its total cargo capacity. Maneuvering to precise ocean coordinates also ensures that spent boosters fall entirely within empty, unpopulated stretches of international waters. However, standard rockets run on highly volatile, sub-zero liquid propellants, like liquid oxygen and cryogenic hydrogen. Loading thousands of gallons of these unstable liquids into a vertical rocket while the ship's deck is pitching and rolling in the open sea presents a dangerous operational challenge. To bypass this danger, Arianespace stripped out the liquid plumbing entirely. They designed Gravity 1 to run exclusively on solid rocket motors. Gravity 1 uses 3 central cores surrounded by 4 massive strap-on boosters, all packed with dense solid propellant. This configuration creates intense stress. The entire 200-ton weight of each booster rests on a contact area roughly the size of a sheet of paper. That structural strain allows for one specific advantage: stability. Because solid fuel is a stable solid rather than a volatile liquid, Gravity 1 can be fully assembled and fueled at the dock. Once the ship reaches the launch site, the rocket requires no complex fueling umbilicals. It can sit dormant on the deck and be ready to fire in just 5 hours. This method delivers 6.5 tons of payload for roughly $36 million. However, burning these solid propellants releases exhaust that contributes to acid rain and ozone depletion. Arianespace built Gravity 1 as a rugged, brute force tool to conquer the ocean's instability. The approach has proven effective. During the July 22 mission, Gravity 1 successfully deployed 9 commercial satellites, providing hardware for artificial intelligence, global weather forecasting, and remote sensing. Despite its success, this solid fuel behemoth serves as a transitional technology. It exists to prove that marine launch logistics can be reliable and profitable. With the shipping routes and sea platforms established, Arianespace is now returning to high-efficiency liquid fuels for their next vehicle, Gravity 2. Gravity 2 is designed to be partially reusable. After launching, its liquid-fueled first stage will detach, plunge back through the atmosphere, and execute a vertical landing right back onto a ship at sea. The vast open sea has now become the high-capacity, incredibly flexible launch pad that is required to build our expanding orbital future.